Okay, this is chapter 11, problem 88. And here we've got a classic static equilibrium problem. We're told we've got a bar with a given length and mass. We're told how it's attached at one end to a wall and able to rotate freely. And we're told there's a cable at distance x from the hinge and making an angle theta with the bar. And then we're asked some questions about the forces involved. So, before we can answer those questions about forces, let's start by drawing a free body diagram. I'm going to start with a bar. And let's say the left end is the wall. So here's our hinge, and we're going to have a vertical component of force, and horizontal component of force treated separately. So we've got let's just call this V, and our horizontal component H. We've got the bar's weight. Coming down, we can treat the weight as coming from just the center of mass of the bar, which is going to be 1 meter from the left end. And we know M and G, so let's just call this M and G. And finally, we've got some cable. The cable could be attached here, could be attached here, could be attached here, and could be attached here. I'm going to draw it in position A, but it could show up in any of these. So we're going to have a tension force coming out at some angle. We'll call this T. And we know here is our theta. All right, so that's our free body diagram. Those are our four forces. Now, this is a static equilibrium problem, so we know that the sum of the torques around any point is going to be equal to 0, and we know the sum of the forces in any direction is going to be equal to 0. So let's see which of those things will be useful to us as we answer these different problems. For part A, we're asked about the strength of the cable, so we're looking for this tension T. And what I'm going to recommend doing to find that is, since we've got these other unknown forces over here that we don't really want to deal with right now because we don't know what they are, let's use the condition that the sum of the torques around an axis is 0, and I'll pick the hinge to be my axis, because that way both the vertical and horizontal components of the force at the hinge produce no torque. So that simplifies our torque equation. Got sum of torques about that axis equals 0. So we've only got two torques here. We've got the torque from our tension force, which is going to be our radial vector of length x times the magnitude of the force T times the sine of the angle between them. Now, you'll notice that the radial vector really comes all the way along the bar and kind of out past the end of it here. This would be our r vector. And our force vector is as drawn. So really the angle between them that we need the sine of is this thing marked in blue. But you'll notice that theta is 180 minus this angle in blue, and the sine of each of those two angles is going to be the same. So we can write our torque as xt sine theta, where theta is the theta that's given in the problem statement. It's not always true that the theta, the angle that you put in your expression, is the angle just given to you as the problem is described, so it's good to check that. All right, that's our torque due to the tension force, and that's going to tend to rotate it in the counterclockwise direction. The torque due to the weight is going to tend to rotate it in the clockwise direction. Opposite, so that's going to be a minus, and we've got here, we know this is attached at 1 meter. going to skip writing the 0.00 times mg. And this is equal to 0, this whole quantity, so I can just set these terms equal to each other. And we can rearrange and solve for T. Retention is equal to 1 meter times 8.5 kilograms. Oops, sorry about that. Times 9.8 meters per second per second squared. And that's going to be the same for all of our configurations A, B, C, D given in the table in the problem. We'll divide that by x sine theta. And so now we've got an expression for the tension, and all we have to do is plug in our values of x and theta. So we can make our little answer table. Got condition A, B, C, D, and the magnitude of the tension in each case. You can plug in the numbers and do the math. What you end up getting is, with tension in newtons, and we're only asked what's biggest and smallest, so I'm going to just round the nearest newton. In case A, we've got 83. Case B, we've got 64. Case C, we've got 184.6, or so 185. And case D, we've got 173. So the problem asks simply in what case, in which of these cases is the tension the greatest and the smallest. So as we can see, it's the greatest in case C and the smallest in case B. All right, moving on to part B. I'm going to step onto the next page. Now we're looking for the horizontal component of the force the bar exerts on the hinge. So if we go back to our free body diagram, now it's going to be useful to us to use the static equilibrium condition that the sum of the forces in the horizontal direction is 0. So we can see we've only got two horizontal forces, this horizontal force from the hinge and the horizontal component of tension. Horizontal component of tension is going to be T cosine theta. So that gives us sum of f in the x direction is equal to our horizontal hinge force minus T cosine theta. And that's equal to 0. And so we've already got our values for tension from our table previously. We're given the angles, so we can just plug in our numbers again. We have H equals T cosine theta. Oops. Let's erase that. Anyway, yeah, plug in your values of tension and other cosine theta, or if you want, you can go back to just our original expression for tension. If you notice, you multiply that by cosine theta, you end up with T equals 1 meter times 8.5 kilograms times 9.8 meters per second squared over x tan theta. In any case, what you get is case A. Can make our table again. B, C, D. Now, got H in newtons. And again, we'll round because we're just looking for biggest and smallest. So in case A, you end up with 72 newtons. Case B, only 32 newtons. Case C, 147. And case D, 45. So now we've got our greatest value in case C again, and our least value in case B again. We can look back, that actually matches our answer to part A, though the numbers are different. And lastly, or almost lastly, part C, we're looking for the magnitude of the vertical component of the force that the bar exerts on the hinge. So now, as you might guess, we're going to use our last static equilibrium condition. The sum of the forces in the y direction equals 0. And if we look back at our free body diagram, we've got 3 different forces in the y direction. Now we've got the vertical component of the hinge force that we're looking for. We've got the vertical component of tension, which is T sine theta. And we've got the weight going down. Now, if you look at our expression for tension here, we take this original expression. If we multiply it by sine theta, you'd get something that depends on x. It doesn't actually depend on theta at all. Let's put this in over here. We've got V that we're looking for plus T sine theta and minus mg is equal to 0. And so we can rearrange to solve for V because that's what we want. And we get that V is equal to mg minus T sine theta. So let's go back and grab our expression from first page. And so we have minus 1 meter times mg divided by x. And so you'll notice, and this is what the hint is getting at in the problem, that this expression is only going to be positive if this term on the right is less than mg, that is, if x is greater than 1 meter. So the vertical component of the hinge force will be upward as we drew it, i.e. V is positive when x is greater than 1 meter, so in cases A and B. In cases C and D, we're actually going to, if we plug in x here, we're going to get a negative value for V, which just means the force has the same magnitude as the absolute value of that negative value, but it's actually pointing in the downward direction. And that's fine. We originally drawing the free body diagram, we just guessed that the vertical force is pointing up because its actual direction is going to depend on the relative magnitude of the weight and the vertical component of tension. So let's again solve for these magnitudes in all our cases. A, B, C, D. And we're going for V in newtons. And we've got A, 42. And this is just you're plugging in the different values of x. B, 28. C, we've got negative 28, meaning it's a magnitude of 28 newtons pointing downward. And D, we've got negative 83, so a magnitude of 83 newtons pointing downward. And we're asked to compare the magnitudes. So largest is D, and smallest, we've got a tie for C and B. So that's the end of part C. Now we're asked, is one of the alternatives given in the table preferable, and should any of the alternatives be avoided? Well, larger forces are more prone to destroy the equipment that you're working with. So basically everything with the smaller forces is going to be preferable. If we look back through our three tables, you've noticed that, look at case B, had the smallest force in all three of the forces we cared about. Case B had the smallest. So I would say that case B is the most preferable case. Looking at things where the force was the largest, it was case D over here. It's actually pretty small horizontal hinge force, but a pretty large tension in the cable, so I probably would not pick D. Case C has actually the largest cable force, also by far the largest horizontal force in the hinge. A low vertical force, but still I wouldn't pick case C either. So I'd avoid C and D. Case A got mediocre vertical hinge force, and mediocre horizontal hinge force, and fairly small force of tension in the cable. So case A might be okay, but as an answer, we'd say alternative B is preferable, would avoid both alternatives C and D. And that's the end of that problem.